Welcome to this video on section 4.3 Lagrange multipliers. So the goal of this section is to minimize or maximize a function. Well, we've already done this in the previous section, but in this case we want to minimize or maximize the function over a certain curve. So instead of looking at a whole area D, we're just going to look only on a certain curve C, and the goal will be to only maximize the function over the curve instead of over the whole area. So the mental example that we're going to use here is the following. So let's say I have some mountainous region, well, in the previous section we wanted to find the highest point of the entire mountainous region, so the highest mountaintop. This would be maximizing the function over the entire area, where now the function is just the height of the mountain. In this case, we're maximizing over a curve, so let's say there are all kinds of paths on this mountain. And now I want to find the maximum height where it can actually go to. And of course, we have to stay on the path. So that means we're looking at the highest point on the path on the mountain. This is going to be the example that we're going to use. For this, we're going to use theorem 126, which I will first explain. So the assumptions of the theorem is that D is a subset of R2, which is open. And now in this case we have two functions, f and g, which are both defined on D, which have continuous first order partial derivatives. So partial derivatives. So the function f here is going to describe the height of the mountain, and g is going to describe the path. So how will g do this? Well, the curve c that we're going to maximize over is going to be precisely those points x and y which are in D, such that g of xy is 0. And this is how we think of the path, and so the path is given as the level set of g, and this is how the function g describes the path. Okay, so now obviously if we want to maximize or minimize this, let me write actually the goal. Let's do this in blue. So the goal is to maximize or minimize a function over a curve. So I want to say maximize my function f over the curve g. Well, we've already seen for that we want to find the extremes. And this theorem is going to help us by finding the extreme points. So we're going to assume that f restricted to c has a local extreme. So either local minimum or local maximum. And now we want to find some conditions in order to find these kind of points. And this local extreme is at the point x0, y0, which is obviously on the curve itself. So maybe a small picture. So I have my area D, then I have my curve C, let's do that in blue. And we have our point x0, y0, which is a local extreme over the curve C, means that it's, for instance, could be a maximum on the curve. So it could be a maximum on the path, a local maximum. But it need not be a maximum over the whole domain D. So there could be points close to it which are still higher. But on the path C, it's going to be a maximum. And this is precisely the amount of the points that we want to find. Because if we have all of those, then we will be able to find the global maximum. There's one more thing that we need, that's a technical condition, is that the gradient of g at the should never be equal to 0, to the 0 factor. And this must be true for all points on the curve. So this is to make sure that the curve is a nice continuous path, otherwise the theorem does not work. And the conclusion is as follows. Then there exists a value lambda naught such that the point x0, y0, lambda naught is a critical point of the so-called Lagrange function. This is why it's called the Lagrange multiplier method. And what is the Lagrange function? The Lagrange function is now a function of 3 variables, so we only had 2. But now we have 3 variables. We have an extra variable lambda, and the Lagrange function is simply f minus lambda times g at the point xy. Okay, so let me explain how we can use this theorem. It tells us that whenever we have a local extreme, it must be a critical point of the Lagrange function. So, therefore, if we find all critical points of the Lagrange function, we're going to find all the local extremes of f. And this, then later, we can just take the maximum of those to find the global maximum. Okay. Just want to say one sentence about the proof. The proof is not examinable. I want to say a little bit about this. The proof is using the implicit function theorem. And how? Well, remember the curve is given by the level set of a function. And the implicit function theorem then allows us to write either x as a function of y on that curve or y as a function of x. And if we're in such a situation, we are similar to the previous section where we had to compute extremes of a boundary. Then we reduced everything to a single variable case, and then we just had to compute the critical points of those, which was just done by taking derivatives. In this case, the function is not explicitly given, but we can still find these derivatives because the implicit function theorem also gives us a way of computing the derivatives. And when you do all of that, you eventually get to this theorem. So this is what is behind it, the implicit function theorem, which also gives us the opportunity to find these single variable derivatives. Now I just want to continue with some remarks. So what is this strange Lagrangian here doing, and what does it mean that that is a critical point of the Lagrangian? So let me now continue with some intuition about the theorem. So this is in the book Remark 1 to 7. So suppose we have such a critical point. So the gradient of the Lagrangian is equal to the zero factor, right? That's what it means to be a critical point of the Lagrangian. Let me write the Lagrangian also here. So the Lxy lambda is equal to f minus lambda g. So that is the Lagrangian. Then if you plug this in, so what is the gradient of the Lagrangian? That's the partial derivatives with respect to x, y, and lambda. So if we take the partial derivative with respect to f, we get the first equation right. That's the partial derivative of the Lagrangian in the x direction, which has to be 0 because that's the first coordinate of the zero factor. So this has to be 0. Similar for the derivative in the y direction of the Lagrangian, which is f sub y minus lambda naught times g sub y. Right, because lambda is a constant when we differentiate with respect to y, and this has to be 0 as well. Now if I differentiate the Lagrangian with respect to lambda, well, the first factor fxy does not depend on lambda, so that will vanish. So that means that the derivative of lambda times g is just going to be g. So it will be minus g at the point x naught, y naught equal to 0. So these are the equations that you have to solve in order to find critical point of the Lagrangian. Okay, so just a small remark. If we take these two equations together, we see that the gradient of f is equal to lambda naught times the gradient of g in that point. Okay. And now I just want to analyze what happens here in this case. And there are actually two possibilities for lambda naught. It could be 0, it could not be 0. So let's write a line and first consider case 1, which is that lambda naught is equal to 0. And in that case, it means that by this equation over here, by this equation over here, we see that gradient of f must be 0 as well. Well, that means that x0, y0 is a critical point of f on the whole domain D. Remember, we're looking for critical points on a certain curve, and this condition is saying that we have a critical point on the whole domain D. So if you think about our analogy with the mountain, it means that we find a critical point not just of the path, but of the entire mountain. So either a local maximum on the entire mountain or a local minimum. Let's continue with this idea of finding the maximum. So this is the first case. In case 2, we consider the case where this is not equal to 0. Well, then again, by this equation over here, if that value is not 0, we see that the gradient of f and the gradient of g are proportional. Yeah? So it means that gradient f and gradient of g are proportional, meaning they are scalar multiples of each other, namely the scalar multiple is lambda naught. Yeah? So we can say something about the gradient of g, and this is by theorem 103. We know that the gradient of g is a normal vector to the level curve. To the level curve of g, we are on a point on the curve. This is already given. Therefore, it's going to be the level curve of g at 0, which is the curve c. So this is going to be a normal vector to the curve c. Okay. Okay, so that's something we know about the gradient of g. Furthermore, by the same reason, we know that the gradient, the gradient of f, by the same reason, is also a normal vector to a level curve of f. But we don't know the value of that function, but yeah, it's gradient. Okay. So now let us make a little bit of a picture. So let's say we have a level curve of f, which goes like this. So this is this thing is level curve of f. We also have a level curve of g, which is our curve c. So this is the curve c. And then, well, we have a tangent line. That is a little bit ugly, so let's try to draw a straight line. We have a tangent line through the point. I'm again not satisfied with this. Okay, that looks better. So the red thing is a tangent line to both of these curves. Why? Well, because we have that the gradients are proportional. So for instance, if lambda naught is negative, then the gradients would go in opposite direction of each other. They could also go in exactly the same direction, but they will be on the same line. They are proportional. Yeah? So the point is that both curves go through this point x0, y0. So that's the point over there is equal to x0, y0. So both curves go through these points, and the normals are parallel. They're in the same direction. And that means that the tangent lines are equal. So what does it mean? It means that the level curve of f and the curve c roughly go in the same direction around my point. So in other words, the curve c exactly goes in the direction of the level set of f. So let's write this down. So the conclusion is that the curve c goes in direction of level set of f. Okay. What does this mean for our analogy with the paths? It means that, remember, this curve C describes the path, and the level set of f, that's where f is constant, so that's where the mountainous region is roughly at the same height. So what this is saying is that the path is roughly flat. So this exactly follows from the mathematics that we did. Of course, this makes sense because we're looking for a local extreme on our curve C. And if the path is not flat, we can always go, one direction in the path will always go higher and the other direction will go lower. This is guaranteed by the fact that g is a differentiable function, so we cannot have kinks like this. So only if the path is flat can we find a possible extreme. And this is sort of the intuitive meaning that we get from this calculation that I just did from this case. So in the end we have two cases. The first possibility is that our local extreme on the path is actually a local extreme of the entire mountain. So in this case the path will go over the top of the mountain. But it may not happen. In that case we need to have that the path has to be locally flat. So flat around this curve. Okay, then there's a remark 128 which I quickly want to discuss. And then afterwards I will discuss the examples. So remark 128 is saying that the first thing is that if the curve is closed and bounded, then we are guaranteed by theorem 111 that we have a global minimum and a maximum. However, it's possible that the curve is not closed and bounded, and then in that case our function may fail to have a global minimum or maximum on the curve. However, in the examples that we will look at, the curve will actually always be closed and bounded. Just recall that if the path is infinite, we may not be able to find the global minimum or maximum. The other comment is about the endpoints. Just like in the previous section, if our curve has endpoints, we have to treat them separately. But I will do this in the example which I will explain in the next in the next video lecture. So with this I want to end the intuitive explanation, and in the next video I will discuss the two examples in the book in which you can see how you can use this method.